Okay, so up to now, we have talked about one way of doing AM transmission, and oh, it's called double sideband. Okay, the name, the reason for this name will be clear when we finish um, this today's discussion. Okay, so as I said in the beginning, we will talk about three ways of doing AM transmission. Okay, now here is the second way. Ah, sorry, I pressed the wrong button. Okay, I'm so sorry. The first way is double side band. Okay, now here is the second way. Um, in fact, it is almost the same. Okay, with a tiny difference. Um, oh, sorry. Wait. Sorry. Okay, as a transmitter, what we'll do is after multiplying by the carrier, okay, I will pass it through to low pass filter. Okay, and now I will explain why later on. And then the receiver is the same. Okay, all right. Okay, so now let, let me explain how this works. Again, um, you assume x of omega as the signal has um, certain spectral shape. Okay. Um, then now let me call this as z of t. Okay, and let me draw the spectrum of z. Okay, would look like this. Okay, because again, Okay. All right. So then it passed into a low pass filter, and I set the low pass filter at cutoff frequency omega c. And so what will happen is that my y, okay, in this case, it just exactly filters out half of the original signal spectrum. Okay. All right. So, and then you send the y of t through free space. And then now let me go through what happens at the receiver. So what happens at the receiver is you receive y, and then you still multiply by cosine omega ct. So therefore, your b of t, okay, it's still y times cosine omega ct. And then so therefore your b of omega is still half of y shifted to the left, and then y plus y shifted to the right. Okay, and so what you will get, okay, supposedly you will get something like this. Okay, and then this is 1/4, and then everything here is 1/4. Okay, now if you're uncomfortable, you can see it this way. So let's say this is the red part, and so then this is where the red part is after the shifting. This is the green part, and then this is the green part after shifting. Okay. All right. Okay, so of course then at the receiver, now this time you have a filter with amplitude 4, then then you get back your x of t. Okay. All right, so now this is not very different from the um, first way of doing things. Okay, and now let me just say the name first. Uh, this is called single sideband. SSB. Okay. Okay, so now I want to talk about why we care. Okay, what's so different about it? Mm, the important thing here, in fact, the only difference is that um, in the first way, we actually for double sideband, we actually transmit z of t. In the second way, we transmit this y of t. Okay, now look at the difference in the spectrum. Okay, so the main reason why we talk about this is because of the bandwidth of the signal between z and y. For z, the bandwidth here, okay, of one signal is 2 omega m. Okay, if you transmit y instead, the bandwidth it's actually omega m. So therefore, the single sideband actually save bandwidth by factor of 2. Okay, all right. I want to make sure we get this technical part correct. Okay, the difference is that by doing single sideband, we can save the bandwidth, the signal bandwidth by a factor of 2. Now, why do we care about it? Now, the reason why we care, okay, is because bandwidth is super expensive. Okay, so now this is something more related to the economics of telecom. So typically, in principle, anyone with a signal generator can multiply some signals by cosine of something and then put an antenna, then you can send it out. Okay, practically, you have to have a license in order for you to send signals at certain frequency range. It is all controlled by the government and related laws that govern the use of the free space spectrum. Okay, so each company pay a lot of money just to get, for example, 5 megahertz of spectrum to provide their services. Okay, so because of that, everyone only have a limited range in frequency spectrum for you to use, and so if you are able to transmit one channel with half the bandwidth, that means you are able to transmit twice the number of channels. That means you can support twice the number of people simultaneously talking on the cell phone. Okay, so that becomes a very big and important increase in the efficiency, both in terms of technology and also in terms of the cost and benefit. Okay, so there is a lot of reasons why we wanted to use less bandwidth to do the same thing. Okay, again, because bandwidth is extremely expensive. I'll upload some related documents to show uh, you know the approximately how much are we talking about. It is a huge number, okay, in the order of hundreds of millions for like 5 megahertz of bandwidth, and you only get to use it for a fixed period of about 15 years, and then you have to release it back out, and then the government will have a bid again, and so this process continues. Okay, so now coming back to what we are talking about here, we use this way the single sideband. The purpose is to do the same thing to be able to do AM transmission, recover the signal, but then you actually take up half the bandwidth. The signal actually take up half the bandwidth while you transmit your signal. Okay, and so that is the point. Okay. All right. Now here it's some more details of single sideband. Let me see if there's a question. Okay. All right. So let me draw this again. No. Okay, so now let me throw a bit more names to this. Now the sidebands actually has two parts. Okay, now this part we call the inner sideband, and this part we call the outer sideband. So in fact, you can actually just transmit one of the sidebands, and then you'll be able to fully recover the signal. All right. So now what that means is there are multiple ways to do single sideband transmission. Okay, passing Z through a low pass filter is one way. As an exercise, you can show that if I pass it through a high pass filter with cutoff omega C, you will still be able to build a single sideband transmission systems. Okay. All right. And then in the homework, we actually have a third way for you to build a single sideband transmission system. Okay, so this will be an exercise. All right. So again, the purpose of I'm sorry, the purpose of having single sideband transmission is because we can save the bandwidth of the signal, okay, by a factor of 2, and we care because bandwidth is very expensive resources. Right? So we always wanted to use less bandwidth, okay, to get our job done. Okay. All right. Okay. So that's the second way, and then now let me go to the third way. Okay. This third way of building AM system, the name is hard to understand until maybe after the midterm. Okay, so for now, I will need you to just memorize this name. Quadrature amplitude modulation, QAM. Yeah, let's not bother explaining what this means at the moment. We'll come back to this after the midterm. Okay, now this is what QAM it's about. So it is also about saving bandwidth, right? In a different, using a different concept and coming from a different angle. So I have two signals. Okay, now in frequency division multiplexing, we talk about how two signals can simultaneously be transmitted. Okay, as long as you make sure when they are carried to some other frequency range, they don't overlap. Okay, now let me propose to you that we can actually do this. Now, this time is the same carrier frequency. Okay, it is the same omega c, but one is cosine, one is sine. Okay. And then I claim I'll just combine together this way. Okay, and then at the receiver, here's what I will do. I will split into two parts. And exact same filter. Okay. Okay, so now let me start by sorry, this is drawn very badly. Okay, so let's have two signals, and the spectrum looks like this. Okay, so let me start by saying y of t is x1 cosine omega ct plus x2 sine omega ct. Okay, So actually y of omega, okay, that will be if you look at the if you look at the equation, so that will be half x1 omega plus omega c half x1 omega, right, the spectrum of x1 shifted to the left and shifted to the right, okay, and then now here it's what x the spectrum of the x2, the spectrum of x2. Now I'll just write down the answers. I hope we'll be able to see why. Okay, so the Fourier transform of x2 sine omega ct is 1 minus 1 over 2j x2 shifted to the left, and 1 over 2j x2 shifted to the right. I hope that is understandable. Okay, that's because sine omega ct is 1 over 2j of e to the j omega ct minus e to the minus j omega ct. Okay, let me just as a recap, let me just write it here. Okay, that is the okay. All right. So then, if I draw this, one, one, half. Okay. Now, how do I draw x2? There are lots of ways. Here, just for illustration, sometimes I just like to draw this way. Okay, it is the original one. Okay, and then the this one times. Okay, so now this may be not so rigorous. Okay, but I wanted to highlight that like in this course, it is important to get the concept right. Okay, so sometimes like for these sort of situations, in principle, uh, we said that spectrum supposedly would have two graphs. One is the amplitude, one is the phase, because the spectrum is a complex number. Okay, but here for our discussion, I don't want, just for convenience, I don't want to draw two graphs. Okay, so I'll just draw it this way. Okay, it is the M-shaped spectrum x2 multiplied by 1 over 2j. Okay, so I wanted to tell you that this is acceptable when it comes to drawing spectrum. Okay, if for for certain questions it is it is it does not really add too much value for you to draw another graph. You can just explain it this way. Okay, so we can accept that. All right. Okay, so now here's the problem. Why if you look at the spectrum of y, okay, um, the two signals actually overlap, x1, x2, the spectrum of x1, x2 overlap. Okay, so but then I'm saying now things will become interesting. This is actually okay, as we will show. So at the receiver, okay, now let's look at what happens at the receiver. So at the receiver you have y, okay, and then you branch into two paths. All right, so let me talk about this path first, b1. Okay, now I wanted to talk about what happens. B1, it's y times cosine omega ct. Okay, and so oops, sorry. Okay, now it's okay, right? Do we have okay? Good. Sorry, I don't know what happened. Uh, Sine of 2 omega ct. Sorry, handwriting is getting bad. You know what? Let me just write it properly. Plus half x2 sine 2 omega ct. Okay, that's because sine omega ct cosine omega ct, that is half of sine 2 omega ct. Okay, all right. So now let's see if we can finish analyzing with the following discussion. Now you have three terms here: half x1t and then half x1t cosine of 2 omega ct, half x2t sine of 2 omega ct. Now let's do a more intuitive discussion. I want to talk about, if you look at the spectrum of B1, which signal would be centered at which frequency range? For example, this signal, half x1t, if I took the Fourier transform, that spectrum of this signal x1, I say it will be centered at 0 frequency. Are we okay? So just x1 of t, if you take the spectrum to the Fourier transform, okay, the spectrum of this particular part x1 of t will be centered at 0. This term would be centered at 2 omega c, and this term would also be centered at 2 omega c. Oh, sorry, I should say plus or minus. Oh, sorry, this is not done well. Let me do this again. Okay, Let's do this again. Let me do this again. Plus or minus 2 omega c. Okay, now I actually skipped one step and I wanted to make sure we are okay. Okay, so I could have draw the spectrum and then illustrate it more clearly, but I'm hoping that we are comfortable enough that we can just discuss and discuss and reason it out with this discussion. Okay, so if I want to look at the spectrum of B1, okay, B1 has 3 terms. Each term, if I look at the spectrum, this term should be centered around 0. This term should be centered around 2 omega c because there's a cosine 2 omega ct here. This term should also be centered around 2 omega c because there's a sine 2 omega ct here. Okay, so then why do we talk about this? That's because at the end, B1 pass through a low pass filter, and I want to say at the end you will be able to get x1 of t. Okay, by scaling the filter amplitude by 2. Okay, are we okay? So I want to make sure we are okay with this discussion. Okay, just by looking at the terms of the time domain waveform, you can actually tell where in the spectrum it is located. Okay, all right. Okay, so now we haven't finished yet. The same logic can be applied to our discussion of B2. So this time it is okay. All right, and then now this will become half of x1t sine 2 omega ct. Okay, because cosine and sine gives you half sine 2 omega ct. Okay, and then you will have half of x2t minus half of x2t cosine 2 omega ct. Okay, that's because sine square is half of 1 minus cosine 2 omega ct. Okay, and so now at this point, by the same logic, and then you pass it through a low pass filter, then you will realize that what remains actually is x2. Okay. All right, because by the same logic, this term, the spectrum, is centered around 2 plus or minus 2 omega c. This term, it is centered around plus or minus 2 omega c as well. Okay. All right. And so now, what have we done here? We have done something that is quite interesting. We actually transmit two signals, x1, x2. Okay, they actually overlap in frequency when it's transmitted to free space. Look at the y here. Okay, yet at the end we are able to separately recover x1 and x2. Okay, so and the trick here is that one of the signal actually goes through a cosine omega ct, another goes through sine omega ct. Okay, and then we show through the math that you at the receiver, if you do the same, you'll be able to separate out x1 and x2 and then recover them separately. Okay, and so this is QAM. This is what quadrature amplitude modulation means. Okay, one signal goes to the cosine, the other signal goes to the sine of the carrier at the same frequency. In that case, you are able to simultaneously transmit and receive um, uh, 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 two channels. Okay, another way to see it, it's that now in this case you actually use a bandwidth of 2 omega m, okay, to transmit two signals. So therefore your so-called bandwidth efficiency is as good as single sideband. Okay, the to transmit two signals. Okay, so the what we call the bandwidth efficiency is actually the same as single sideband. Okay, so you can see this as a way to also save bandwidth. Okay. All right, and so the things that we talk about here, especially for AM transmissions, um, don't think that this is such an old thing and there's no practical relevance anymore. In fact, whatever we discuss um, up to this point is actually the most fundamental know-how or this fundamental aspects of building the state-of-the-art communication systems. Okay, so in modern days, X1 of t is not your voice anymore. It's not just radio station. X1 and X2 of t can itself be high speed, like 1 terabit per second transmission digital signal, okay, which we will talk about after the midterm. Okay, the transmitter and receiver structure is the same. Okay, just that in modern days, X1 and X2 is not analog information anymore. It is high speed digital information. So we will come back to this QAM thing very often when we talk about digital transmission. In real life, uh, all your signals, all the digital signals in your computer, your cell phone, whatever, all this stuff are actually based on uh, combination of frequency division multiplexing and QAM, and then a little bit of single sideband transmission as well. So all these three concepts actually will we are actually using all of them in modern day telecom. Okay, and so yeah, so this is the the application or context that I wanted to share with you. Okay, all right. And so in this case, you know what? Yeah, because there's the curriculum is slightly different from last year. In fact, I want to say this is pretty much all I want to talk about today. Okay, so we can actually break a bit earlier today. Okay, usually we will talk about FM, but then I think let's just wait until next week to talk about FM. Okay, so we can we can break a bit early today. So actually, no, sorry. Yeah. So in case yeah, let's just break off, and I'll see you again next week. Please start to take a look at the lab sheet and also at the past midterm questions, and then I'll update you on the actual logistics of the midterm throughout the week and also in the class next week. Okay. All right. Thank you so much, and we'll see you each other again next week.